Bismillahirrahmanirrahim. Today we are talking about the exercises for chapter 1. Now, in the previous sections, we have almost covered so many things. So we are doing this book, A Concise Introduction to Pure Mathematics by Martin Liebeck. And we have covered this chapter 1, in which we have talked about sets and then proofs. And we have talked about some basic set theory, and then we have talked about like the ways of proving the statements. So there were few different ways, and we have proved given a proof by contradiction. We have given a proof by disproof by counter example, and we have also given a way of proving the statement directly. Now we will talk about, and this all have covered in last three lessons on this lecture, like on this course. So if you want, you can go and watch them. Now we will talk about the exercise 1. And the exercise 1 says that we have set A, which is a set A be the set of alpha, and the set contains 1 alpha, 3 in the set, and then there is another set which contains 1 3, and then we have, yeah, so eventually there should be another bracket, right? Okay, then we have the statements. What statements? So A, statement A is alpha is inside. Statement B is that alpha in the set is not inside A. Statement C is 1 comma alpha is a subset of A. Statement D is that the set 3 and the set containing 3 is a subset in A. Then now, if you talk about these, so you can see alpha is an element as an element inside A. So this is true, whereas alpha in the set is not an element inside A. So this is false. Yeah. So not an element inside A, and this is true also. Now, step for the C. 1 comma alpha is a subset of A. It's not a subset of A. It is an element inside A. So this is false. 3 comma the set containing 3, and then the set again which contains 3 is a subset inside A, and this statement is true because if you can see, yes, if you can see from here, it is true. Then we have few more statements. So sorry, E, statement E is that 1 comma 3 is in A. Statement F is that the set which contains another set is a subset of A. Statement G is that 1 comma alpha is not in A, and statement I is that phi is a subset of A. Now, you can see 1 comma 3 is here, but it's not inside A as an element. It is inside as an element in the other set, which is inside as an element in A. So this is false. Again, this set is not a subset in A, it's an element in A. So this is false. Now, 1 comma alpha is an element inside A. So it is in A, but this says not in A. So this is also true. Now, phi is inside A is a subset, which is true. Okay. Question number 2. Which of the following statements are true and false? So let's write that. Statement A is n is 3 only if n square minus 2n minus 3 is 0. Statement B is n square minus 2n minus 3 is 0 only if n is 3. And statement C is if n square minus 2n minus 3 is 0, then n is 3. Now, the way we are solving these or doing these is actually changing the whole scenario. And if you think about it, that for the let me select this part and move a little bit further. Right. Now, if we look at this, so this is so for the statement A, n is 3 only if n square minus 2n minus 3 is 0. Now, to show that whether this is true or false, A. If you solve this equation, what we will get? So we will get that to solve n square minus 2n minus 3 by the quadratic formula or like the factorization or like something that, then we will get n square minus 3 n plus n minus 3 is 0. And if I open it further, it will be n into n minus 3 plus 1 n minus 3 is 0. And I can write this further like n minus 3 into n plus 1 is 0. Now, from the property that product of two things is 0 if and only if they are greater than 0, then there must be one among them which is 0. So by this rule, we can write n minus 3 is 0 and n plus 1 is 0. Then we have n is 3 and n is minus 1. So if from here, we can say that n is 3 only if this equation is equals to 0. So this says that A is true. So this is true. Now B. B says that this equation is 0 only if n is 3. So B says n square minus 2n minus 3 is 0 only if n is 3. Now, to cancel this out, we take n is minus 1 and put it into this equation. So minus 1 square minus 2 into minus 1 plus 3 is 0. And this shows n square is plus 1, minus 1 square is plus 1, and then minus into minus plus 2. Sorry, this is minus, and minus 3 is 0, and this is 0 is 0. This shows that because there is some other number that this equation is 0 for, so there it's not necessary that only if n is 3, this is 0. So B says I am false. Okay, right. Now the statement C. Statement C is if this equation is 0, then n is 3. Well, for that, it's not necessary again we can do that when we solve this equation, n have two values, one this and then this. So it's not necessary that if this equation is 0, then the only value of n is 3. There is only value, so n is also equals to minus 1. So false. Okay. Now there is part D, which says that for integers a and b, ab is square, ab is a square only if both a and b are squares. Okay. Now, to solve this, we can take something like A and B are 2. Then AB is 2 cross 2, which is a 4. So when but A comma B are not squares while AB is. So the answer is false. So there is a major difference between there's a major difference between using only if and then using if only. So let's see the part, actually not C, but the part E is for integers A and B. AB is a square if both A and B are squares. Now, this statement D says AB is going to be an square if only, so only both are squares. That's not a case. It's not necessary that if these are squares, then only their product will be square. So this is an example that these two are not squares, but their product is a square. So there is no need to put only. If we remove the only from here and we just say if both are squares, then see how will it will be the statement. So see, if A and B are squares, then let's say A is m square and B is n square with m comma n from integers, then AB is going to be m square n square, and you can write it mn square, so which is a square. So if you remove the only and then just say A and B are squares, then the product will be in squares. That's fine. But if you say if only if these two are squares, so with the only, there are many numbers which are not a square, but their product is a square. So this is true. Okay. Part 3. Question number 3. Question number 3 says disprove the following statements. Statement 1 is if n and k are positive integers, then n power k minus n is always divisible by k. And to disprove it, what we can do? So we can do for part A solution. Let's take n is 2, k is 4, minus 2 is 14. Let me more write it clearly. So n is 2, k is 4, then 2 power 4 minus 2 is 14, and not divisible by 4. Hence, the statement is false when n is 2 and k is 4. So this statement is false. Part B, every positive integer is the sum of 3 squares. Every positive integer is sum of 3 squares. Let's just try a counter example like this. So let's say 7 belongs to the positive integers, and 7 is not the sum of 3 squares. So this shows false. Question number 9. Question number 9 says that in this question, I'm assuming you know what a prime number is. So if you want, I can write. Can I write here? Yeah. I can write what is the prime? So prime is a number who is only divisible by, let's say P is a prime if the only divisors of P are plus minus 1 and plus minus P. Okay, this is a definition for the prime. Now, if we assume this knowledge, then for each of the following statements, form is negation and either prove that the statement is true or prove that its negation is true. So for all n in Z, for every integer n such that n is a prime number, n is odd. Negation. Let's try the negation. A. This is a solution. So A. To form its negation, we said there exists an n in Z such that n is a prime number and n is even or not odd. And this negation is true. This negation is true is n is equals to 2 is an even prime. Perfect. Number B, part B says, for every integer, there exists A, B, C, D, E, F, G, H in integers such that n is the cube of all these numbers. And to form its negation, what can we do is we say that there exists some n in Z such that for all these A, B, C, D, E, F, G, H, and Z, the number n is not the cube of all these numbers. E cube, F cube, G cube, H cube. Now the original statement is true. The original statement is true. And how we do that? So to do that, let's write the original statement is true. What is the statement? Every integer is the sum of 8 cubes. That's very interesting. And this is tricky to prove, but here's the proof. So let's say n be an integer. Let n be an integer. Then n cube minus n is a multiple of 6. Now this is a proven statement already, that if you cube a number and then subtract the number from itself, it will be a multiple of itself for any integer, like every integer. So you can try that. So let me just try an example for this statement. So let's say we have 2 cube minus 2. And this is the simplest one. This answer is 6. And then for 3 cube minus 3 is just 27 minus 3, that is 24. So on. So this statement is already true. So for every n in Z, n cube minus n is a multiple of 6. Okay. Then write n cube minus n as n cube minus n as 6x with x is going to be an integer again. Okay. Now observe that if I cube a bracket with x plus 1 cube plus x minus 1 cube, that will be 2x cube plus 6x. And hence, if I write n is equals to n cubed minus 6x, from the equation, I can write that from this equation, this one, because, or even this one, we can write this further as n cube minus x plus 1 cube minus x minus 1 cube plus 2x cube. Why? Because we know that this expression is actually equals to 6x. From this, we can write an expression for the 6x. Yes. So this is true. And then we can write that thus n is in fact the sum of 5 cubes. In fact, the sum of 5 cubes. Notice that it is crucial in this proof to allow negative cubes. If we insist on all of the cubes being non-negative, then the negation is true. It's not going to be equal to. So for example, 23 is not the sum of 8 non-negative cubes. 23 is not the sum of non-negative cubes. So it is very necessary that n should be equal to, so n can be the sum of positive and non-negative cubes. So it's the sum of 5 cubes and then it's going to be the sum of 8 cubes. Similar process. What we can just do is to expand this more. Right, okay. Then let's do the part C. Part C says, okay, I can't paste it here, but that's fine. I'm gonna just write it with this. There exists x in Z such that, C says, there exists x in Z such that for all n in Z, x is not equals to n square plus 2. For all n in Z, x is not equals to n square plus 2. Let's try to prove this. First, the negation. Negation is going to be that for all x in Z such that there exists n in Z, x is n square plus 2. Now this negation is also false. Is false. So for example, let's take x is 4, and you cannot write this in the form of some n square plus 2. So the original statement is true. The original statement is true. Right? Now, part D. Let's write the part D. Part D is almost same, just we remove the square from the statement. So that is, there exists x in Z such that for all n in Z, we have x is not equals to n plus 2. There is not equals to, right. Okay. Now to solve this, we have negation. And to negate this, we have for all x in Z, for all x in Z, such that there exist n in Z such that x is equals to n plus 2, and the negation is true at this time. So this statement is true. How? Take n is equals to x minus 2. You just have to take n is equals to x minus 2. You will get that. Now part E says we have a set. We have a set. Says for all y inside a set x such that x in Z, where x is greater than or equal to 1, 5y square plus 5y plus 1 is a prime number, is a prime number. To negate this, we can say there exists a number y in the set. It says that in the set for which this equation, this expression is not a prime. And this negation is true. You can show that. So this negation is true. So let's say if y is 12, then 5y square plus 5y plus 1 is 5, 12 square plus 5, 12 plus 1 is 781, which is not a prime. Which is not a prime is it is multiple of 11. So you can divide this by So one time, 7 time, it will be 77, and then you will pass 1, so that will be 71. So this answer is 71. Right. Okay. Now the part F says for all y in the set x square is less than 0, then 5y square plus 5y plus 1 is a prime number. Remember, we need to take the y from this kind of set, okay? So then solution and negation would be that there exists y inside the set such that this equation is not a prime, and this negation is false because this negation is a false because is the set in the equation in the question is an empty set. Is the set in question is empty. So the original statement is true. Thank you so much. I'll see you in the next lecture, and that will be on the number systems. So remember, we are doing a course on the concise introduction of pure mathematics, and this is not the way we used to do the maths in first year and inter. This is how we try to do the maths in the undergrad or like university degree. Okay, and there will be all those proofs in the next part. Y under root 2 is not a rational number. Like if a and b are rational numbers, if a is a rational number and b is an irrational number, what is the sum of these two? Why it is their sum is irrational? How many irrationals there are? And we can all talk about the different proofs. Like there is a real number alpha such that its square is 2. How we can do that? There is between any two rationals, there is another rational, and to do that, how we can try to find that. So all those statements and then proofs, and then we can do the exercise for that. So take care.